This assessment asks us to predict the product and show a mechanism of the reaction on screen. Well, when we look at this, what we first notice is we have two aldehydes, right? Two aldehydes reacting with sodium hydroxide, water, and heat. Those sound a lot like the conditions of an aldol reaction. The difference here is that it's going to be intramolecular because we could conceivably make the enolate on one side and have it react with the aldehyde of the other, right? So we could do a ring-forming reaction. Well, let's start along those lines and see what comes up. Thinking, let's just try to do an intramolecular aldol and see if that gets us to the right place. We can start by removing the proton. These electrons go there, pushing those electrons onto oxygen. That's going to make the enolate. So starting the way all aldol reactions do, by making the enolate. Draw in the two methyl groups. And at this point, you're probably wondering, hey, this is a mechanism problem. Why aren't we numbering the carbons? Great idea. Let's number the carbons because that's going to help us in terms of how we draw the structure. One of the bigger challenges that students encounter is when we take intramolecular reactions, how do we draw what we've created in the new product? Numbering carbons is going to make that really easy. So now we've got an enolate. We've got an aldehyde. These electrons are going to come down. They're going to push the pi electrons out to attack carbon 6, which is going to push the pi electrons onto oxygen. Now, again, I said drawing this product can be hard. We can make it easier by keeping our carbons numbered. And what we notice is we're going to make a bond between carbon 2 and carbon 6, right? So if we think about drawing this, let's just go ahead and draw that we have made the 2,6 bond. So we'll do it this way. We'll put carbon 2 down here, carbon 6 here. What we also notice by connecting carbon 2 and 6 is if we count between them, we have 1, 2, 3, 4, 5 carbons that are in the ring. And so we can go ahead and take this carbon 2, carbon 6 idea and turn it into the 5-membered ring that we've created. Right? This process here is not about understanding the chemistry, but it's how do we take the arrows that we've drawn and the story that those arrows tell and translate it into this product. All right, well, now we can just continue the numbering. To get from 2 to 6, we go through 3, 4, and 5. So there's our 5-membered ring made up of 2, 3, 4, 5, and 6. At this point, we're just ready to decorate, right? We can now decorate the ring. Well, coming off of carbon 2 is carbon 1. There's carbon 1. And carbon 1, we just formed the new CO double bond to give us our aldehyde back. So carbon 2 at this point is attached to the aldehyde of carbon 1. Right? What else is happening? Well, there was one more hydrogen at 2. That one is done. At carbon 3, we have a methyl group. That methyl group will be up. At carbon 4, we have another methyl group. Now, this one's a little bit trickier because it was a bold wedge. It was coming towards us in this picture, but when we rotate around the 3-4 bond to put it in this conformation, so the conformation changes when we go to a ring, it was bold wedge. Now it is going to be dashed. That's maybe a concept for a different video. Just trust me on that for now, that by rotating around that bond, we get that group down. That group is now down. Don't get so caught up in that. That's not as important for this particular problem. Carbon 5 was a CH2. It's still a CH2. Carbon 6 had a hydrogen, and it now has an oxygen. But that oxygen, instead of being double bonded, is single bonded, and now has a lone pair, 3 lone pairs, and a negative charge. So by numbering the carbons, we make sure we're drawing the right product, okay? At this point, we can just continue the normal aldol process. We can remove a proton from water. That's going to be what regenerates the base catalyst and also gives us this alcohol here. Draw the aldehyde in, put in our decorative methyl groups. We would be done if we weren't heating the reaction, but because we're heating the reaction and we usually heat the intramolecular reaction, we drive it to completion through this heating. Because we're heating it, we know we need to eliminate the hydrogen from the alpha carbon and the hydroxyl group. So we can do that by first forming the enolate. So hydroxide will remove a proton, push these electrons up to make this enolate. When you're doing these complex mechanisms, it's always a good idea to step back and make sure we have drawn everything. So we've got our methyl groups, we've made our enolate, still our 5-member ring, we still have the hydroxyl group. At this point, the enolate can collapse and push these pi electrons over to kick out the hydroxide in the step that eliminates hydroxide. Remember that eliminating of the hydroxide is going to regenerate our base catalyst and also give us the product of this reaction. So we reform the aldehyde. We now have a pi bond here. Let's not forget our methyl groups. Put our methyl groups in. This is the product of the intramolecular aldol reaction, and here is the mechanism.